If I told you, it's not true that I'm both tired and hungry. Am I saying the same thing as I'm either not tired or I'm not hungry? It sounds like a word game, but in mathematics, things are not always what they seem. A statement might look long, intimidating, and confusing, but it might actually be saying something incredibly simple. It's like a secret code waiting to be cracked. In this video, we are exploring logical equivalence, the art of proving that two different looking propositions are actually twins. We are moving beyond just true and false to discover how we can transform logical statements without ever changing their meaning. We will learn how to strip away the complexity using truth tables and logical laws to find the core truth hidden inside. By the end of this, you will see why logic is the ultimate tool for clear thinking.
I will explain about logically equivalent. So, the meaning of logically equivalent is when two statements have the same logical content. There are three ways to prove that two statements are logically equivalent. First, we can show that their truth tables are identical. Second, the biconditional of the two statements must be tautology. And the third way is we show that the two statements are contrapositive to each other. Next, there are three forms of related conditional to the statement P implies Q. The first one is converse, where we exchange the position of antecedent and consequent so it becomes Q implies P. Next, inverse. We obtain this form by negating antecedent and consequent so it becomes not P implies not Q. Lastly, contrapositive, which is not Q implies not P. We get this form by negating and interchanging the statement P and Q.
First, by using the truth table, determine whether P implies Q or P implies R is logically equivalent to P implies Q or R. Second, write a conclusion for the statement. Firstly, spread the statement into a small statement. Fill in the truth table with the 8 combinations of truth value in P, Q, and R. Fill the truth table with the truth value to complete statement will get it from a combination of the other statement. Lastly, find out if the statement is tautology. Now, we can already know that all the statement is a true. So, they have two options to write a conclusion. First conclusion is the 6th column and 8th column are identical. So, P implies Q or P implies R is logically equivalent to P implies Q or R. Second conclusion is last column show that biconditional for two statements is a tautology. So, P implies Q or P implies R is logically equivalent to P implies Q or R.
Alright, now I will continue with example 2. Here, we are given the statement, if it's rain then the ground get wet. For this statement, P is it's rain and Q is the ground get wet. First, let's look at the converse. To form the converse, we switch P and Q. So the converse is if the ground get wet, then it's rain. Next is the inverse. For the inverse, we keep the same order but negate both P and Q. So the inverse become if it does not rain, then the ground does not get wet. And finally, the contrapositive. To form the contrapositive, we both swap and negate P and Q. So, the contrapositive is if the ground does not get wet, then it does not rain. The statement has the same true value as the original conditional statement. To conclude, in logic, every statement is either true or false. The most important thing is to correctly identify P and Q and to understand how to form each type of conditional statement, which are the converse, inverse, and contrapositive.
So we have last example. For this example, we are given two statements. The first statement made by Aina is if nasi kabur expensive, then it must taste good. The second statement made by Olmi is if nasi kabur tastes good, then it must be expensive. Now, we want to determine whether these two statements are logically saying the same thing. At first glance, these two statements might sound similar, but logically, they are actually not saying the same thing. Let us define P as nasi kerabu is expensive and Q as nasi kerabu tastes good. Aina's statement can be written in symbolic form as P implies Q, meanwhile, Auni's statement can be written as Q implies P. Here, we can see that Auni's statement is the converse of Aina's statement. In logic, the statement is not necessarily equivalent to its converse. For two statements to be logically equivalent, one must be the contrapositive of the other. The contrapositive of Aina's statement, which is P implies Q, would be not Q implies not P, which is if nasi kerabu does not taste good, then it is not expensive. Since Auni's statement is not the contrapositive of Aina's statement, but only its converse, we can conclude that the two statements are not logically equivalent and do not mean the same thing.
We have seen today that the way we phrase a problem can change its look, but it doesn't have to change its truth. Logical equivalence gives us the tools to look past the surface of an argument and see its underlying structure. To truly understand the theory of logical equivalence, we must look at the biconditional. Theoretically, two statements are equivalent if and only if their biconditional relationship is a tautology, a statement that is true by its very form, regardless of the word around it. This is the beauty of logical laws, like De Morgan's or the distributive laws. They are not just rules to memorize, they are truth-preserving transformations. They allow us to navigate the map of logic without ever losing our way. We have seen today that logic is not just about finding what is true, it's about understanding the invariant structures that make true possible. Thanks for watching. Bye!